Okay, this is 3.2, concavity and the second derivatives test. Concavity helps to determine if an extrema is a maximum or a minimum. We found that using the first derivatives test. Now we're going to have some more tools to find out whether an extrema is a maximum or a minimum. First, let's define concavity. Concavity comes from the word cave. So when concave up means that the cave is going to open up or whether it's going to open down. Here's an example of a concave up, and this is concave down. Okay? Alright, kind of simple. Here's a more technical way of defining concavity. Is concave up if the graph lies above its tangent lines. And is concave down if the graph lies below its tangent lines. Alright. Let's see here. For the second derivative, if you take the second derivative and it happens to be positive, then it's concave up. Second derivative is negative, then it's concave down. This relates to our first derivative, in that the first derivative is positive, means that the slope is going upward, increasing. And if the first derivative, not the second derivative, first derivative is negative, that means it is decreasing. Okay, and there's one more case here. You have to remember that besides being positive or negative, it could be equal to 0. Well, when it's equal to 0, then that graph is linear and it's not concave up or down. If you think of a linear line, then that one is not going to be concave up or down. Alright. Here's an illustration of concave down and concave up graph. Now, here's that concept that we were trying to get across earlier in the year. We're first talking about derivatives. Here's the graph of f, and here's the graph of its derivative. And we've lined them up by its domain, the x values, so that we can see that this is going to be a large positive slope. And that positive slope is going to be a large number, and it's going to get smaller and smaller until it gets here, where it's going to get smaller and smaller and get to 0. The slope is 0 right here, and the slope is going to be small negative, larger negative, until it gets to here, and it's the most negative right here, and then it becomes less and less negative until it gets to this point, right? And then it becomes 0. That's the slope. So it's going to be the most negative right here, and it's going to get less and less negative until it gets to 0, and then the slope starts becoming positive again, and it's going to be small positive right here, and it's going to get larger and larger positive as it goes away from that minimum point right here, which is this point right here. Alright, so that brings us to the point of inflection. The point of inflection, the POI, is where it changes direction. It went from a concave down to a concave up. Concave up looks like a happy face because it's curved upward. Concave down, it looks like a sad face because it goes downward. And it's going to go down, 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 down until this point right here, where it goes from sad to happy, right? This is the point where it becomes a happy face from the sad face. So this is the point where it changes from concave down to concave up. Or if you're thinking about the technical definition, the tangent lines are all going to be above the graph up here. And then somehow it becomes the same as the graph here. And then the tangent lines become below the graph, right? Okay, the tangent lines are above, or the graph is below, and now the graph is above the tangent lines. Okay, and then we have the point of inflection is where the second derivative is 0. Okay, so let's see. Here's the second derivative. Now I've done the same thing. I just took the slopes of this line and I drew it down here. Now I take the slope of this and put it down here. So the slope is negative, negative, large negative, 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 and it starts getting smaller negative, right? Negative, 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 and smaller negative until it gets to a 0 here, and it starts becoming slightly positive, more and more positive, more and more, slightly positive, and more positive as it's going away from its minimum point of 0. So that's how we use the second derivative to find the point of inflection. We set the second derivative to 0 and we find the point of inflection. Then we just test each side of it to see whether it's going to be negative or positive. If the point of inflection is here and I test, let's say, a -1 and it's negative, I know that it's going to be concave down. And if I test a point on this side, let's say a +1, and it's positive, I know it's concave up. This is more graphs of points of inflection. So here's the happy face, concave up, and now point of inflection, the POI, now becomes a sad face. Now it's concave down, concave down, concave down. Right here is where it becomes concave up. So we have zeros for the second derivative. We don't see the second derivative like we do here, but if we did, we would see a 0 here and here. And this is going to be concave up because it's going to be positive. The second derivative is going to be positive here, negative here, and positive on this section. So you're going to break it up into 3 pieces using 2 points of inflection. You have the left piece to -infinity, the middle piece between those 2 points, and then the third piece that's to the right to the positive infinity end from this point here. Okay, there's a case where it doesn't change. There's not a point of inflection, but you still have the second derivative is equal to 0. It's going to be positive, positive, positive. The second derivative is positive, even though this is negative, right, for decreasing. But second derivative would show that this is positive, positive, and it's still going to be positive on this side. So it will be just concave up, never concave down, even though there's a 0 point on it. Okay, let's do one here. We have this problem here. First, we're going to have to find the derivative. Okay, finding the derivative. So we start by rewriting this. You know how I like to keep these things simple when I take the derivative. So rewrite it as an exponent. So I'm going to leave that 6 alone because that just interferes with what I'm trying to do. So I'm going to have to use the chain rule here. Take the derivative and then use this u thing here. This will be -1 from the -1, and then we have to take the derivative of the inside. Okay, cleaning this up a little bit. I have 6 times -1 times 2x, which is -12x, and since this gets the negative exponent, that goes in the denominator. So that's my second derivative. Now if I want to do this as that's my first derivative, and take my second derivative, I will do the quotient rule here, and that's going to give me the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Chain rule again. Let's see here, that would be 1, and then the inside will be 2x all over x squared plus 3 to the 4th. Okay. Now, I see x squared plus 3, x squared plus 3. I have 2 of them here. Now, I'm going to rewrite this kind of a clever way. This will help you out here, I believe. I'm going to write this like this with a negative 12 minus. You're going to multiply this. That's going to be a positive 24x squared. No, actually that's 48. 2 times 2 times 12, that's 48. Alright. Times x squared plus 3. Alright. All over x squared plus 3. Okay, I did that because I could see I have a bunch of x squared plus 3's here. So I have 1 here, so I'm going to eliminate 1 in all of these. Okay, so I'm going to eliminate 1 of these, make that a 3, make that a 1. Okay, now I'm going to finish simplifying this. Okay, now this will be 12 negative 12x squared minus 36. And this is just 48x squared all over x squared plus 3 cubed. Combining my like terms. And then I can actually factor out a 36. Alright, so that is my second derivative. Now, if I want to make this equal to 0, I don't have any places where it's going to make it discontinuous, but I do have some zeros up here. So I can make the numerator equal to 0. Divide both sides by 36. And factoring this, difference of squares, so I get x is equal to a negative 1 and a positive 1. So now I'm going to make my little table here. I get my first point of inflection is negative 1. My second one is at positive 1. Those are my points of inflection. And then I'm going to test some kind of value. So I'm going to test. I'm going to find the sign of my second derivative, and then I'm going to test, let's see, something smaller than negative 1. How about negative 2? And then between negative 1 and 1 it would be 0 and positive 2. And the sign of the second derivative, let's see, we're going to go back up here to the simplest form of the second derivative is right here. So I'm going to plug in a negative 2. Well, if I plug in a negative 2, the denominator is going to stay positive. Negative 2 up here, that's squared. So that should be positive, right? Positive minus 1, positive, positive, everything's positive. All right. 0, 0, that's positive. 0 minus 1, that's negative 1 times 36. That's negative over a positive. And then this 2, 2 squared, that's going to be 4. 4 minus 1, that's positive, and everything else is positive. So I have concave up, concave up, concave down. Okay, it asks us for the open intervals where it's concave up and down. Okay, so concave up, I have from negative infinity to negative 2, and also, oh sorry, negative 1. I was looking at that. So my points of inflection from 1 to infinity, and then concave down, I have from negative 1 to positive 1. So that's how we use the second derivative to find the concavity. Alright, next example. Alright, let's try this one. Remember, we'll have to get the second derivative, so we'll start with the first derivative. This one's not going to be as much fun, I don't think. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Simplifying this, I get 2x cubed minus 8x minus 2x cubed minus 2x. All that over. Okay, in my like terms, the 2x cubed and negative 2x cubed, and then that's my first derivative. Now I get to do it again. Second derivative. Okay, I have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, chain rule. All over x squared minus 4 to the 4th. Okay, now I'm going to try to cancel one of these here. So I think I can go ahead and do that now, if you don't mind. Okay, now I'm going to simplify. So this is going to distribute that, negative 10x squared plus 40. And then this is minus minus, that's positive 10x times 4x, which is going to be plus 40x all over x squared minus 4 to the 3rd. Factor out a factor out a 10. I think I lost something here. Let's see, this is 10x squared minus plus 40, and this is going to be that's good. So that's going to be x squared. Yes, there it is. Okay, so now I get 30x squared plus 40 over x squared minus 4 to the 3rd. Factor out a 10, 3x squared plus 4 over x squared minus 4 cubed. That's my second derivative. Set that equal to 0. You can't make the numerator equal to 0 no matter what I put in here because I square it, right? So, but I do have two places where this thing is going to be discontinuous. So I set the denominator equal to 0. Cube root both sides. Factor. And I get x is equal to 2 and negative 2. So, making my table. Alright, so negative 2 and 2. Now this is not really a point of inflection because this part is not continuous. Remember, points of inflection, POIs, are places where it switches from concave down to concave up or up to down. But this is actually an asymptote. These two are from the denominator, an asymptote. The graph, just giving you a quick sketch of what the graph looks like. The graph is going to be two things like this and then one piece down here. And this asymptote at negative 2 and positive 2. So that's what we're looking at here. So we can still have concave down, concave up. We just don't have points of inflection. So now we're going to test and find the sign of the second derivative. So I test negative 3, 0, and positive 3. Putting, let's say, negative 3 in here. Negative 3 is going to stay positive up here, and then the negative 3 will be positive down here because negative 3 squared is 9 minus 4, so that's going to be positive. 0 is going to give me a negative down here, and then the 3, for the same reason, this is going to be 9 minus 4, that's going to be positive. Okay, so concave up, concave down, concave up. So you're going to write concave up as negative infinity to negative 2, then from 2 to positive infinity, and then concave down, it will be from negative 2 to 2. Alright, next example. Okay, find the points of inflection this time and discuss the concavity of the graph. So in order to find the points of inflection, we've been doing this already. We're going to take the second derivative. So this one is nice. No denominators. Yay, and no chain rule. Alright. Second derivative. Squared minus 24x. Okay, and just cleaning this up just a little bit, I get 12x x minus 2. Alright, so if I set this equal to 0, I get a 0 and a positive 2. So those are my 2 points of inflection. And now we're going to test the concavity. So doing the same thing again, 0 and 2. Those are my, now we know that these are my POIs. They come from the numerator. When they come from the numerator, they're POIs, points of inflection. When they're from the denominator, they're points of discontinuity. We're going to test. Let's see, how about a negative 1, 1, and a 3. And then my sign of my second derivative, negative 1 in here would give me, negative 1, that's definitely a positive. and then a positive 1, that would be a negative. And then 3 would be 9. 9 times 12 minus 3 times 24, that's positive. So we have concave up, concave down, and concave up. Alright, so now let's talk about the second derivatives test. Okay, the second derivatives test. So once you find the critical number from the first derivative, when you plug that into your second derivative and it's positive, then your critical number, or your critical point now, this is a critical number and this is a critical point. The critical point is going to be a minimum. If your second derivative is negative, then your critical point is going to be a maximum. If your critical number produces a 0 in the second derivative, then the test fails. Then you have to go back to the first derivatives test. Now, a lot of people don't use the second derivatives test because we have this problem where sometimes it doesn't work. They go directly to the first derivative. But I like to use it because it's kind of quick, especially if you can take the second derivative easily, like the last problem we just did. That's a real quick way to find out by solving the first derivative for 0. Even we didn't solve that first derivative for 0 to get my critical number, to get my critical points to try, but if we did, we can very quickly and simply get our relative minimum or maximum. Sometimes it doesn't work, okay, if it's equal to 0. So it either has to be positive or negative. If it equals to 0, that means we have to try something else. So we're going to do one. You notice that this one is nice and easy to take the derivative of twice. So I will definitely use the second derivatives test for this problem. Alright, so here we go. First derivative will give me a negative 15x to the fourth plus 15x. Simplifying this a little bit, I get, how about negative 15x times x to the third minus 1. Okay, that's my first derivative, and since I'm looking for the critical number, I'm going to set this equal to 0, and I get x is equal to 0 and 1. And let's see here. Let me think about this for a second. Oh, no wonder. All right, I forgot that right there. So this is actually going to be squared, and this is going to be squared. And I'm going to get a plus and minus 1 here. That's the difference of squares. All right. Were you screaming at me because you caught that mistake? Okay. Good for you. You were really paying attention, or you were awake. Alright, so those are my C values with my critical numbers. Now I'm going to take my second derivative, and I'm going to do it from here. I'm not going to use the product rule, okay? I hate to disappoint you, but alright, I'm going to do it from here, so that'll give me a negative 60x cubed plus 30x, and I'm going to factor that out a little bit and get 30x, and this will be, how about negative? Yeah, keep this one positive for me. 2 minus 1, yay. And then I'm going to set that equal to 0, and I get, I actually don't need, to set this one for 0, because I'm using the second derivatives test. Okay, all right, so okay, so I'm going to plug in these in here, and if it's positive, it's going to be a minimum, and if it's negative, it's going to be a maximum. Okay, alright, so putting that in here, I get 0 and 0. Let me see, let me just put these back in here first. 0 and 0, so I get a 0, 0. And a 1 would give me negative 3 plus 5, so that'll be a 2. Negative, no, positive 1 and 2. And put the negative 1 in here, that will be a positive 3 and a negative 5, so that'll be a negative 2. Alright, now we want to find the sign of my second derivative. Sign of my second derivative at 0. At 0, this is going to be 0. So that's no good. And then at 1, this will be 1, negative 30. And that's going to be a negative number, right? 1 does mean negative 30, and 1. That also gives me, that can't give me a 0. Let me see, 1 here. That'll be 30, and that will be a minimum, because this will be negative. And then put a negative 1 in here. I get a positive 30, and positive 60 minus 30, that's positive. Alright, so this is going to be maximum, a minimum, and this is where the test fails. Okay. So, since the test failed here, then you just have to apply the first derivative test on either side of 0, and then you'll be able to tell if this is a maximum or a minimum. Believe that this is neither a maximum or a minimum. Yeah, this is, if I test this, this is not going to be a maximum or a minimum, because it's going to the first derivative. If I test like a negative 1 in here, right here I would test it, right? Here's my 0. I would test a negative 1 and a positive 1. Negative 1 in here would make this negative, and this would be positive. So that would be 0, and then a 1 would make that 0. So this is not a minimum or a maximum. That's okay. That's not going to work here. But the reason why this is so is because the graph looks like this. There's a minimum, and then it kind of just hovers over, and then it continues on like that. So at 0, it's not really a point of inflection. It's increasing and it keeps on increasing. Okay. And then here's the maximum. Here at 1, 2. The minimum at -1, -2. And here is not a minimum or maximum. Alrighty. So, if you could do problems on page 195, number 5 and 6, I'll pick out a couple easy problems for you to practice with, and then find the points of inflection for number 19, and then use the second derivatives test on number 39. 3, 4 nice, easy problems, not too taxing. Okay, this shows that you understand what you're watching here. Thank you so much.